Hello! In the context of the Roots of Polynomials chapter, it's in your interest to know some formulas to aid you with some calculations. As a result, I'm aware that some of you who are watching this video will be doing so just for revision purposes, and so I will be including a timestamp in the description so you're able to skip ahead to the part where the formulas are being shown rather than staying around for this initial explanation. But what are we talking about? Well, if we are, for instance, dealing with a quadratic that's got roots of alpha and beta, where, as usual for the Roots of Polynomials chapter, you're not actually calculating what alpha and beta are individually, you could be asked to calculate the value of alpha squared plus beta squared. And how are we going to do that? Well, it probably wouldn't take you that long to realize that if you start with alpha plus beta and you square that, of course, unfortunately, it doesn't mean you can just square the individual things inside the brackets. You've got to fully multiply out the brackets. And therefore, if you multiply everything by everything else in the other bracket, you'll eventually end up with alpha squared plus 2 alpha beta plus beta squared. What this means is we can realize that alpha squared plus beta squared is just going to be equal to the sum of the roots squared minus 2 lots of the product of the roots. And there you go, you'd be able to find that very easily. For those of you who've watched videos on my channel before, you'll know that in the context of preparing for an exam, I'm not a fan of using formulas for everything, because ultimately you just have to end up remembering all those off by heart, which can come at the cost of understanding what's going on. And therefore, I'm acknowledging that in scenarios as simple as this one, you might be able to get away with just figuring it out in the moment like we did here. However, the inconvenient truth is that for this topic, there are formulas you do need to know just because you're not given enough marks or therefore time to be able to manually figure out more complicated combinations of alpha and beta for exam questions. I'm talking about, for instance, scenarios such as this, where you have to work out the value of alpha squared plus beta squared plus gamma squared for a cubic or something. Because the problem is, although you could again realize that it's going to be related to the sum of those roots then squared, the actual act of having to manually multiply out those brackets, now that there's 3 variables inside them, is just going to take you a lot longer, and as I said, you don't have the time to do it. And it gets even worse if you're asked to calculate something like alpha cubed plus beta cubed plus gamma cubed, because multiplying out brackets involving a power of 3 is even more of a pain. However, therefore, as a result, these are the formulas I would expect you to remember off by heart. The first one is for working out the sum of the squares of the individual roots, which is this. And then also the other formula is for working out the sum of the cubes of the individual roots, which is this more horrible looking one here. I'll let them linger on the screen for a couple of seconds. However, something I would like to acknowledge is that the notation here can seem a little imposing. So just as a reminder, when I'm talking about the sum of alpha squared, I'm talking about the individual roots being squared, then added together. So if you're talking about a quadratic, it would just be alpha squared plus beta squared. But the advantage of these formulas and writing them in this particular way with this particular notation is they can adapt if there are more roots. So the sum of alpha squared means alpha squared plus beta squared plus gamma squared if we're talking about a cubic, and also plus delta squared as well if you're talking about a quartic. The thing is, those formulas do adapt and change depending on what scenario you're looking at. So therefore, in the context of just alpha squared plus beta squared, the scenario we already looked at, I was saying that was the sum of alpha all squared minus 2 lots of the sum of alpha beta. Therefore, that is, in this context, just going to be alpha plus beta, the sum of the individual roots, all squared, because those are the only 2 roots, and then minus 2 lots of the sum of alpha beta, but the sum of alpha beta just means the sum of all the products of the pairs of the roots, but there's only one pair of roots, so it is just alpha beta. Whereas, if you have alpha squared plus beta squared plus gamma squared, it's still sum of alpha all squared minus 2 sum of alpha beta, but that is now meaning alpha plus beta plus gamma all squared minus 2 lots of the sum of alpha beta, which is now going to be the sum of all those combinations of the pairs. So that is this. And so therefore, just remembering the formulas in the format I showed is giving you secretly all the formulas for the quadratic, cubic, and quartic all at once. Now, something I would like to acknowledge, which is for the cubic one, which is that, first of all, yes, it is an absolute pain to remember, but therefore that's partly also why we do remember it, because actually working this out on the spot with all the brackets being multiplied out would take you a really long time. But it's worth acknowledging there is one little thing you've got to be aware of, which is that if you're dealing with a quadratic, this doesn't exist. If you're dealing with a quadratic, you only have two roots, and therefore there is no gamma. Now, I'm not going to say treat gamma as if it's 0, because that's implying there is a gamma and it's got the value of 0. And that isn't what's happening. There just straight up isn't a gamma, and therefore you would delete this bit for just the scenario where you're doing alpha cubed plus beta cubed. But the rest of it still applies as usual, and it scales up for both quadratics, cubics, and quartics as well. And actually, it's because of quartics that it's a good idea to write these formulas using this more scary looking notation involving sigma, because it's an absolute pain to write out all the combinations of the pairs of the roots and the triplets of the roots for quartics, because there's just lots of different combinations to write out. Now, it's worth mentioning for those of you who've studied binomial expansion, that can help a bit with remembering these formulas, partly because that helps you remember why it's the number 2 in that formula for the sum of the squares of the roots, and also why that number 3 appears in the formula for the sum of the cube of the roots. But that's just something to be aware of. Anyway, with that said, let's take a look at some examples. So first of all, we've got this cubic, and we've got to find the values of alpha squared plus beta squared plus gamma squared, and alpha cubed plus beta cubed plus gamma cubed, and of course, it's just a case of using the formulas. In reality, there's not actually that much for me to say here, but it's just a handy way to confirm that what I said works in the way you expect it to. So first of all, working out the things we need, which is first of all working out the sum of the roots, which of course is always minus b over a, where b and a are the coefficients of the original cubic that you're dealing with. So sum of alpha would be that, sum of alpha beta would be c over a, which would be 7 over 2. And lastly, the sum of alpha beta gamma, though of course that's a bit silly, because of course sum of alpha beta gamma for a cubic is just alpha beta gamma, because there's only 3 roots. But to stay consistent with the notation, that's why I'm writing it like that. But anyway, that will be minus d over a, which conveniently comes to positive 6, which isn't too bad. But therefore for part A, we know that alpha squared plus beta squared plus gamma squared is just asking us to do the sum of the roots squared. So therefore that's just going to be equal to the sum of the roots all squared minus 2 lots of the sum of the pairs of the roots. So therefore that is just going to be minus 3 all squared minus 2 lots of 7 over 2, which conveniently will just be 9 take away 7, which is just 2. Really easy to work out. So very quick, and that's why you ultimately need to know the formulas, because it speeds all this stuff up. Part B, alpha cubed plus beta cubed plus gamma cubed. Of course, that is just that other formula we showed, and so therefore we just got to realize that's going to be the sum of alpha all cubed minus 3 lots of the sum of alpha times by the sum of the pairs, plus, controversially, that's another thing that catches people out, it's always plus 3 lots of the sum of the triplets, if there are 3 roots. As I said, if this is a quadratic, you won't have to do that last bit. But anyway, therefore, this is going to be minus 3 all cubed minus 3 lots of minus 3 lots of 7 over 2, and then it's going to be plus 3 lots of 6 on the end. That will come to 45 over 2. And there you go, we're done. Now, ultimately, I'm going to go through more examples now, but if you feel like by this stage you get what's going on, then good news indeed. But for those of you who want more sort of examples of what's going on, I will continue. So for instance, we now have a quadratic, although as I said, you could work these ones out from scratch. In reality, if you know the formulas, it still works on these as well and helps speed up the process, because you instantly know for this first one, we just have to use, of course, the sum of alpha, which is just minus b over a. So that's just 1/5. And the sum of alpha beta, which in this case is just alpha beta, which is just going to be minus 3 over 5. But therefore, alpha squared plus beta squared is just going to be 1/5 all squared minus 2 lots of minus 3/5, which will just come to 31 over 25, assuming I've typed that into the calculator correctly. And then onto alpha cubed plus beta cubed. As I said, it's the formula we've already shown, but of course acknowledging that there is no triple root product that you can work out. So therefore it's just going to be the sum of the roots all cubed minus 3 lots of the sum of the roots times by the sum of the pairs. So therefore we just have to do, in this case, 1/5 all cubed minus 3 lots of 1/5 times by minus 3/5. And that will come to 46 over 125. Cool, so that's showing how you've got to adapt the formula for the sum of the cubes when doing it with a quadratic equation. But our final example, I'm going to go through a quartic, just because although it's still more of the same, that's partly the point I'm making. If you remember the two formulas I showed, then you're sorted pretty much for all these sort of calculations. With a quartic, it looks more complicated, and certainly writing out the formula fully would be an absolute pain to do just because of the number of combinations involving alpha, beta, gamma, and delta you've got to do, particularly with the pairs of the roots. But the formula in the notation we wrote before is the best way to remember it because it works and scales up even for a quartic. So first of all, starting off by working out the things we're going to need to know, which is, for instance, the sum of the roots, which is minus b over a, which is conveniently just 10. The sum of the pairs of the roots, which is just c over a, which is just 35. And the sum of the triple product of the roots, which is just going to be minus d over a, which is conveniently just positive 50. Now you could work out what the sum of the quadruple product is, which I'll write down just for reference. Here is just 24, but we're not actually going to have to use that to work out what we want, because we just want alpha cubed plus beta cubed plus gamma cubed plus delta cubed. But that is just the formula that we have already been using up until now. It's still just going to be the sum of the roots, all cubed, minus 3 lots of the sum of the roots times by the sum of the pairs, plus 3 lots of the sum of the triple products. It's only for the quadratic that you get rid of that last bit, just because there isn't a third root to involve. Therefore, it's going to be 10 cubed minus 3 lots of 10 lots of 35 plus 3 lots of 50. And conveniently, that will come to 100. Cool, and that is therefore all the examples I want to show you. But before we go, I do just want to quickly acknowledge that in some resources you might see a reference to remembering formulas for situations such as this, and I would argue that is not worth the effort, just because this is now going back towards scenarios where I feel that people can start to just work it out for themselves in the situation, in the moment when they're coming across it. Although you are welcome to learn a formula for it, I just don't think it's worth the effort. For instance, if you need to work out this, of course we realize we just have to add the fractions back together, and the way you do that is you create a common denominator, and you do that by multiplying all the roots together, and then as part of doing that, you have to do the same to the numerator as you do to the denominator, and so therefore you end up multiplying by each of the pairs of the roots from the other fractions. So therefore you're going to end up ultimately just adding all the combinations of the pairs of the roots on the top. So yeah, by all means you could learn that as a formula, but it doesn't take that long to work out just by adding the fractions back together that is what you're going to need in order to be able to work this out. Nice, so that's all we needed to cover for today. For those of you who live in England and are studying further maths A-level or AS level, there is a playlist to all the core pure content on my channel, so you can see all the topics you need in one handy convenient place. Goodbye!